All right, welcome to start of chapter 10 about gases. Gases are really interesting in terms of their physical properties um, compared with solids and liquids slash solutions, which we've talked mostly about in terms of the chemical reactions we've conducted in the class so far. To the big sort of defining properties that are interesting about gases is one, they're compressible. So compressibility is this idea that if you've got, you know, let's say a canister, and then in that canister you've got some gas and you've got a piston on top of this thing, right? You can compress this piston, and you know that if you've got some gas molecules in here, that piston will actually compress, right? What's happening when the compression occurs? Well, the distance between these molecules inside the gas is getting squeezed closer and closer and closer together, right? But we know that without getting too nuanced here, if we tried to do the same experiment with, say, a solid or a liquid, and we tried to compress down on this, we wouldn't get any compression, or very minimal compression, depending on some more advanced topics. But gases are generally compressible, right? We can get a gas, say, in a canister, like helium. Maybe you've had this like at a party or something, and you want to use this to, say, fill up a balloon. It's not a bad balloon, right? This canister right here is under high pressure. So this volume of this canister, even though it's fairly small, it can produce thousands of these balloons at a different pressure. Or why is that? Well, the molecules inside this tank are really, 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 really tightly packed together. Not so tightly that they're a liquid, but pretty close. And then the molecules inside the balloon are much further apart. And so pressure and volume are intimately related. We're going to have to talk about that. The other physical attribute of gases that's different from solids and liquids is that they're homogeneous. And this is interesting because it means that they mix completely. So if, for example, you imagine the room that you're in right now watching this video, if you were to take, say, a perfume bottle, I don't know what a perfume bottle looks like, maybe it looks like this, and spray this stuff outward into your room, at one end of the room, what would you expect to happen over time? I think we all have an intuition that a person that's standing way over here at the edge of the room, eventually they're going to smell whatever you sprayed all the way on this side of the room. Why is that? Well, that's because of this property of the homogeneity of gases. If we put some gas molecules into another gas container, say that's the room that you're in, and we release some way down here, if we give time, to infinity, allow enough time, we assume that this gas will completely and fully mix itself throughout this space. And that's true for most gases. That's not true for solids and liquids. And so both of these properties are really interesting, and they give rise to different metrics by which we think about gases, like volume, like pressure, which we'll introduce here in a second, which ultimately is going to give rise to this whole new relationship that, if you've taken a chemistry class before, then you've heard all about this thing called the ideal gas law. And that's really what we're going to get to in this chapter, using the ideal gas law to think about all the variables that are used to measure or control gases, things like pressure, things like volume, things like amount, or the number of moles of something, and the temperature of the system. So really that's the outline of the chapter. So we all have this intuition, I think, of what pressure is, but let's define it from the molecular perspective. So pressure is this exertion of force of molecules on the walls of a container. So if we look at a container, it's this sort of cube here that we've got, and all the red dots are molecules that are bouncing around this container. Just like we thought about temperature, temperature is a measure of molecular motion as it collides with a wall. The force that's being exerted on the side of the wall, the force per unit area, in fact, is the actual pressure. So these molecules, as they ricochet off the wall, like being shown in the version over here, that's what pressure is. So when you've got a balloon like this, the reason it's maintaining the shape that it has is because all of those molecules there are rapidly colliding with the wall of the latex, and they're doing so frequently that it's maintaining the diameter and width of this thing, the balloon, over time. So pressure, in any sense, P, we'll call pressure, is defined as the force being exerted per unit area. In this case, force is measured as mass times acceleration, if you remember from Newton's laws, over area. If we want to think about this in terms of the units of pressure, we can think about this as mass is measured in kilograms, acceleration in meters per second squared, and area in meters squared. So we could write this whole thing out and just do sort of a dimensional analysis to see what the units of pressure look like. That would give us kilograms per meter squared over meter squared. All I'm doing is substituting the units for those different quantities into here. That would get rid of the meter here and the meter here, or just the meter squared, not the actual full meter. That would only get rid of one of those. That would give us a value of kilograms per meter second squared. I'm just putting this down to the denominator in the new version here. This unit, kilogram per meter second squared, we call that a Pascal, which we shorten for PA for short. And a Pascal is, if you go back to the very first video, this is the SI unit of pressure. So this is the basic unit. There's lots of units for pressure, which we'll talk about in a second, but this is one of them that we'll talk about here. So if we think about atmospheric pressure, which is the pressure pushing down on you right now, that's the stuff that's holding you, not the gravity, the force that's pushing down on you, but the air pressure that's pushing around your body on all sides of your body at the same time. So what does that come from? Well, it's really no different. We can think about you on the planet way down here. I don't know what country this is, but you're standing right there. That's you. Perfect. That's you right there. Think about what's above you. So look up above you right now. You don't see anything, but everywhere above your head, all the way until the atmosphere thins out above you and turns into outer space, is a big column of air. What is air made of, right? That's this sort of cone here. This is a column of air. What is air? It's not a vacuum, right? A vacuum is an absence of molecules. Air, there actually is stuff there. So this is all of the nitrogen and the oxygen and the water and the CO2 and all the other stuff, all these molecules that are above you. And this extends for about a kilometer before it starts to thin out and turn into outer space. So imagine that's you down there, and above you is this column of air that is a meter across. So a meter across is about, if you hold one of your arms out, That's from maybe the tip of your fingertips to the center of your chest. That's about a meter. So that width of a circle on top of you, that's the column that extends this whole kilometer upward. So I'll draw sort of a column. That's the column, and you're standing underneath of it down wherever you are. And there's a bunch of stuff in there, right? It's not water, it's not a liquid, but there's still stuff. That's the air. How much does that weigh? Well, you can do the math a couple different ways, but this way it turns out to be about 10,300 kilograms. What is a kilogram? Anybody know what a kilogram is in pounds, if you're more familiar with pounds? If you're more familiar with kilograms, you may. So a kilogram is about 2.2 pounds. So if I just do a quick dimensional analysis here to convert these two things, I can figure out how many pounds this is. It's a lot. I did a quick Google search here, and I figured that an Asian elephant weighs about 8,800 pounds. So I could say there's 8,800 pounds per one elephant. Let's see how many elephants of air mass you have sitting above you at any given moment in time. So it looks like that's 2.6 elephants. You've got anywhere from 2 to 3 Asian elephants. Note that the African bush elephant weighs quite a bit more, but the African forest elephant weighs a lot less. So this is a pretty average elephant size. So you got 2 to 3 elephants that are pushing down on top of you right now, simply in air mass. That's just the mass of the air that's pushing down on you. That's incredible, right? So if we think about pressure, then we can think about the force. We can multiply the mass times the acceleration, which is gravity, 9.8 meters per second squared, divided by the area, in this case, the 1 meter squared, that is this sort of circular disc pushing down on you. And that equates to 101,000 pascals, which is atmospheric pressure. That's what we feel. And note that, you know, if you are in a country that's or a part of the country that's close to sea level, then it should be apparent to you that, let's say this is the world and this is the sea here. If you're standing here, the column of air on top of you to get to outer space, we'll say outer space is way up here, right? That distance above you is higher than if you are standing on the top of Pikes Peak in Colorado, where that distance is quite a bit less, right? Or if you are flying around in an airplane here, and that's you way up there at 35,000 feet or so of cruising altitude, then the pressure, the air pressure pushing down on you, is considerably less. And so this is why altitude or elevation is a strong function in terms of computing what the overall pressure is. So when we think about atmospheric pressure and we think about 101,000 pascals, we're thinking about that for this person here at sea level, and this number gets significantly less if you're sitting right here in Colorado Springs, or if you're sitting up here at the top of Pikes Peak, or you're sitting way up here at the top of Mount Everest, or you know, the cruising altitude for a typical commercial airliner. So this is pretty incredible, right? You've got the mass of these three things, these giant elephants pushing down at you all the time. Why don't you get crushed? Well, that's because your body, I'm not going to be able to draw this, but just imagine your body right now is actually, it's under pressure itself, and it's pushing outward every which direction. All the liquid in your body, all the gases in your body are pushing out in every direction right now to resist the force of all of these elephants that are weighing down on you in an equal and opposite way. That's why if you were to be a human at, say, sea level, and you were to sort of climb a rope all the way to outer space without a special suit, what's going to happen to your body? Well, in outer space, there is no molecules, or the molecules are very, very, very few between, so there's almost no air pressure, which means the force pushing in on you is no longer there, but your body is still exerting force outward, which is why under less and less pressure, your body will start to swell. You would even notice this if you've ever gone to high elevations or high altitudes. Your body may start to swell. Your fingertips may feel more taut. Your face may look more taut as your body starts to expand slightly and adjust to the lower atmospheric pressure that's pushing down on it compared to where you were at sea level. So this is a good description of what air pressure is, what pressure is, and how you sort of relate to it intuitively. So as I mentioned before, there's lots of units of pressure. We'll use many of them, so we'll have to do some unit conversion, but I'm going to introduce you to a couple that are pretty common. So pascals are the SI unit. That is 101,000 pascals. That equals 1 atmosphere. Atmosphere being atmospheric pressure at sea level on this planet. We also use this unit called millimeters of mercury. That comes from sort of the classical way to measure atmospheric pressure. And so I've got a sort of experimental setup here. It's really simple. And you can still do this. You can take a vat of mercury right here. So just a shallow beaker filled with liquid mercury and an inverted tube here that's sealed at one end. So it's just a thin glass tube. And what you can do is as the pressure pushes down on this tube, the atmospheric pressure, remember this is air with mass, it's pushing down on this, it's going to force liquid mercury up into this tube up to a certain height that's above that of the bed of mercury. That pressure turns out to be exactly 760 millimeters high for mercury at 1 atmosphere of pressure. So this 1 atmosphere is the same as 760 millimeters of mercury, which is the same as 101,000 pascals, which often gets truncated into 10 to the 5th pascals when people are talking about this and don't need sig figs. They're just doing a quick conversion. But you can imagine you don't have to use mercury here. Mercury is really nice because it's non-compressible, but and it doesn't evaporate. But you could also fill this dish with water and do the same thing. So Americans often like to use inches of water instead of millimeters of mercury. Don't use this. You may see this come up, but this is not a practical unit of measure, even though some people use this. So converting between units, you shouldn't be too scared of this. There's one other unit here called bar, which is often used. So 1 atmosphere is equal to 1.013 bars. So these are all different units of measure. They're all equivalent and people use them interchangeably.